For more than a century, modern concrete has been treated as the final answer to structural durability. Entire cities have been built on the assumption that reinforced slabs, poured footings, and industrial cement represent the peak of construction knowledge. Yet across earthquake zones, floodplains, mountain regions, and frost-heavy climates, a quieter reality continues to challenge that belief. Ancient stone foundations are still surviving where modern concrete repeatedly fails. This is not a romantic claim about lost civilizations possessing mystical engineering secrets. In many cases, ancient structures collapsed, eroded, or disappeared entirely. But the systems that survived reveal something modern construction often ignores. Long-term structural stability depends less on brute strength and more on adaptation to the environment beneath the structure itself. Many modern foundations fail because they are designed to resist movement completely. Ancient stone bases often succeeded because they accepted movement as unavoidable and built systems capable of surviving it. That distinction shaped the durability of roads, temples, military fortifications, bridges, and entire cities across multiple civilizations. The civilizations that endured understood that the ground beneath a structure was never truly stable. One of the most overlooked realities in historical engineering is just how much labor ancient societies devoted to terrain preparation before construction even began. Archaeological studies consistently show that ancient builders spent enormous amounts of time studying soil behavior, drainage patterns, frost depth, and seasonal water movement. Roman engineers, for example, rarely trusted surface soil alone. Before roads, forts, or public buildings were constructed, workers excavated unstable material and replaced it with layered stone, gravel, crushed aggregate, and compacted fill. These layers distributed weight gradually while allowing moisture to escape through the system, instead of becoming trapped beneath rigid surfaces. Modern concrete often behaves differently. Water infiltration beneath slabs creates uneven expansion, frost heave, erosion, and gradual settlement. Once tension forms inside rigid concrete, cracks spread outward through the structure. Roman systems approached the problem from another direction entirely. Instead of attempting to create an immovable slab, they built flexible, layered foundations capable of dispersing pressure and draining water over long periods. That philosophy explains why sections of Roman roads remain intact after nearly 2,000 years. The same principles appeared far beyond the Roman world. In the Andes, Incan builders faced one of the harshest construction environments on Earth. Earthquakes repeatedly struck mountain settlements where rigid masonry structures failed catastrophically. In response, Incan masons developed dry-laid stone foundations using interlocking blocks fitted so precisely that mortar became unnecessary. These foundations did not eliminate movement during earthquakes, they absorbed it. During seismic activity, individual stones could shift slightly while maintaining overall structural integrity. Energy dispersed across the system instead of concentrating inside rigid walls. In some regions of Peru, Spanish colonial buildings constructed later with mortar-based techniques suffered repeated earthquake damage, while portions of the underlying Incan stonework survived beneath them. This was not accidental craftsmanship. It reflected generations of environmental adaptation shaped by repeated observation and failure. Ancient builders understood something industrial construction often forgot during the 20th century. Absolute rigidity can become a weakness under changing environmental conditions. Military history demonstrates this principle repeatedly. Fortifications built on poorly prepared ground rarely survived long campaigns regardless of wall thickness. Medieval engineers understood that drainage trenches, compacted earthworks, and stone foundations mattered as much as towers or battlements. Water undermined defensive walls long before siege engines breached them directly. During prolonged warfare, ground conditions often became decisive factors in survival. In Northern Europe, castle builders confronted frost expansion, seasonal flooding, and unstable clay soils. Instead of relying solely on continuous rigid foundations, many castles rested on deep rubble trenches filled with compacted stone. These systems dispersed moisture while allowing gradual settlement without catastrophic cracking. This flexibility mattered because military structures were expected to endure decades or centuries of environmental stress. By the 20th century, wartime construction faced similar challenges on a much larger industrial scale. During the First World War, trench systems collapsed constantly when drainage failed. Artillery emplacements sank into unstable ground. Concrete bunkers cracked when rushed construction ignored soil preparation. Engineers discovered repeatedly that terrain itself could destroy defensive systems even before enemy fire reached them. The battlefield exposed an old reality that ancient builders already understood. Poorly prepared ground eventually defeats even the strongest structures. This lesson extended into civilian survival as well. Ancient settlements rarely appeared randomly across landscapes. Communities often selected elevated terrain with natural drainage and stable subsoil. Entire civilizations survived because they understood the long-term relationship between water, terrain, and structural endurance. Modern development frequently reversed that logic. Industrial expansion encouraged rapid construction across wetlands, flood-prone plains, and unstable soils because modern materials created the illusion that geography could always be overcome mechanically. Concrete became, a kind of universal solution, applied across radically different environmental conditions. But the long-term consequences are now showing up in things like cracked foundations, shifting roads, retaining wall failures, and, repeated infrastructure repairs across so many regions. What ancient systems lacked in speed, they definitely made up for in environmental awareness. One of the least discussed aspects of historical construction is actually the physical process of compaction itself. Before there was any mechanized equipment, laborers would compact soil manually, using these heavy tamping tools made from wood, stone, or iron. The objective was simple but absolutely critical: eliminate air pockets and stabilize the substrate before putting any structural weight above it. Loose soil, you see, settles unevenly over time, and once differential settlement starts beneath a rigid structure, cracking just becomes almost inevitable. That principle, interestingly enough, remains unchanged today. Whether you're preparing a gravel foundation for a rural outbuilding or stabilizing a roadbed, modern builders still rely on compaction to create durable load-bearing surfaces. A tool such as the 8x8-inch steel tamper with a 48-inch handle, heavy-duty hand compactor tool for leveling soil, gravel, sand, asphalt, ground, paver, driveway, garden, yard, and blacktop repair, that actually reflects a process ancient builders would immediately recognize. The materials might be different, but the mechanical principle is, honestly, pretty much identical to the historical ground preparation methods used in road construction, fortification building, and stone foundation work across the centuries. Ancient construction was slower partly because, the consequences of failure were just so much more severe. A failed bridge isolated trade routes. A collapsed granary threatened famine. A weakened fortress endangered entire populations during invasion. Builders simply could not rely on rapid industrial repair systems or standardized replacement materials. Structures had to endure environmental stress because, honestly, survival depended on them. That kind of pressure produced construction cultures focused heavily on durability rather than speed. Japanese temple builders developed another important variation of this philosophy. In earthquake-prone regions, wooden superstructures were often placed atop carefully balanced stone bases rather than being rigidly anchored deep into the ground. Controlled movement during earthquakes allowed buildings to survive shocks that destroyed, less flexible systems. Modern seismic engineering eventually rediscovered many of these same principles. Expansion joints, segmented supports, flexible anchoring systems, and base isolation techniques all reflect the understanding that structures must sometimes move with environmental forces, rather than resist them absolutely. In many ways, modern engineering has slowly returned to lessons ancient builders learned through centuries of observation. This does not mean ancient construction was universally better than modern engineering. Modern materials have solved enormous problems related to scale, sanitation, transportation, and urban density. Reinforced concrete remains one of the most important construction materials ever developed. But the historical comparison reveals something significant about the assumptions behind industrial construction. 20th century engineering often prioritized speed, standardization, and mass expansion. Ancient builders prioritized long-term environmental compatibility because they had fewer ways to compensate for mistakes later. The result is that many ancient stone foundation systems continue functioning precisely because they were designed around local terrain conditions rather than imposed uniformly across every landscape. That lesson matters now more than ever. As modern infrastructure faces increasing strain from flooding, temperature instability, soil movement, and aging materials, engineers are revisiting principles ancient builders considered fundamental from the beginning. Drainage-first construction, permeable substrate systems, flexible foundations, and layered aggregate bases are once again being recognized as essential rather than optional. History repeatedly demonstrates that durable construction begins underground long before walls become visible. The foundations that lasted were rarely the strongest in absolute terms. They were the systems most capable of adapting to water, pressure, movement, and time. Ancient stone bases succeeded not because they resisted nature completely, but because they worked with environmental reality instead of pretending it could be ignored. That is the deeper reason some structures still stand centuries later, while modern concrete around the world continues to fracture, settle, and fail. And it is why studying forgotten engineering practices is not simply an exercise in nostalgia. It is a reminder that resilience has always depended on understanding the ground beneath civilization itself. If you enjoyed this exploration into forgotten engineering history and the practical lessons hidden beneath ancient structures, subscribe to History Vault and share this video with others interested in survival knowledge, historical mysteries, and the systems that quietly outlast empires.